Okay. So moving on to the next topic here. Apparent velocity and slip versus rolling contact. Okay. So you might recall from the last topic that apparent velocity takes place when you have something moving, one link moving on another link. Okay, so you're talking about relative displacements with respect to the other link it's moving on usually, okay? And so you have the global coordinate system in which all the vectors are defined with respect to. And if you recall, if you take, and first of all, there's always a point on this link P3 and then a point on the same link that's directly below it. It's coincident on P2, below P called P2. And they always start at the same point, but then some delta t later, you can see with the primes, that means that time has passed. P2 and P3 are no longer coincident. P3 moved from being coincident with P2 to over here. So if you take the displacement delta rp2 of point P2 on this bottom link, you get that. And then you have to add that to the apparent displacement of P2, which is delta apparent displacement of P3, which is delta rp3 / 2, meaning relative with respect to 2. So it's the displacement from P3. If you were an ant sitting on here relative with respect to this, you don't even know this link moved, you would just see the displacement from here to here of P3. So if you add that apparent displacement plus that absolute displacement of P2, you get the absolute displacement with respect to this of point P3. Okay, so that's just a review of last time. And if you divide these by delta t, then what you get is average apparent velocities, but then you shrink the delta t to 0, or approach it to 0, and you essentially get instantaneous velocities. And so this is the apparent velocity equation. So there's no magic here. It's quite obvious. It's just you take the velocity of the point on the base link and add it to the apparent velocity relative with respect to that link of the link on top, and that will be the absolute velocity of that point of that link on top, right? So that's just like, if I'm driving in a truck and relative with respect to the truck, I throw a baseball at you on the ground at 20 miles an hour, but the truck's driving 50 miles an hour, well, that ball's going to hit you at 20 plus 50 miles an hour, right? So 70 miles an hour. So you want to add the relative velocity plus the absolute velocity to get the absolute velocity of the final thing. Okay, that's kind of obvious. Okay, so now we'll talk about slip versus rolling contact. Okay, so whenever two bodies are in contact, they have the same velocity component along their common normal. So if you have two bodies here, so consider these two bodies, first of all, if they're in contact, then they're obviously touching at a point here, and you can draw a line normal, normal to that contact and tangential to it, so 90 degrees from the normal. And what I just said is the thing that defines if they're in contact is that the velocity of this point on this and the velocity of this point on this have equal velocities along this normal line. And you might say, well, why is that the case? Well, if they didn't, if this point on this body and this point, same point on this body, had different velocity components along this line, they wouldn't be in contact for very long. They'd either go through each other, which they're not allowed to do, or they'd separate. So as long as they're in contact, whether they're not moving or moving, their velocity at that contact point in this direction has to be the same. So that's a critical insight. Or another way to look at their apparent velocity is 0 along the common normal. So if you were an ant on this one, meaning you basically think of this one not moving, then the velocity of this point on this body along this common normal would basically be 0. So the apparent velocity, so if this is 3, this would be VP3/2 equals 0, okay? Along that normal, that component. Okay? Okay, so when the bodies are in sliding contact, their velocities along the common tangent are different. Okay, so if the bodies are sliding, so imagine this is like if you're driving on a road and that's rolling, and then you slam on the brake and the car actually starts sliding. The wheel stops rotating, it just slides on the ground. That's sliding, which obviously you can't do if there's gear teeth, right? So gears are always in rolling contact. But if you're just two cylinders on top, you could be sliding or rolling. And so if you're sliding, that means your velocity in the tangential direction is not the same, okay? So and of course, they're not. If they were the same, then these guys would not be moving relative to each other. But if they're different, then they're actually sliding, right? So it's kind of obvious. Okay, and that's to say, their apparent velocities are also obviously different, not zero in this direction. So the apparent velocities are not zero. Okay. Okay, so what I basically just said, if you now think of this scenario here, we have this link of a weird shape. It's link 3 and this link 2, and then there's ground with pins here. Of course, for this to be a mechanism to move and not be a structure that's locked up, this has to have 2 degrees of freedom, sliding and rolling. And remember, just review, this is a mechanism, but it's not a linkage, because there's a higher pair here. Okay, but anyway, that's not the point. The point is, these are in sliding and rolling contact. And remember, for the case of rolling contact, okay, if two bodies are only rolling, then the apparent velocities of both, okay, Vp3 with respect to 2 and Vp2 with respect to 3 have to be 0. Okay, because because if they're in contact at all, the velocities along this direction have to be the same, which means the apparent velocity has to be 0. But if they're sliding, the apparent velocities must not be 0. So if both the component of apparent velocity along this direction is 0 and in this direction is 0, then that's rolling contact. Okay, which also is another way of saying the velocities of both those points are exactly the same in either direction. Okay. So I think I described that a little confusing. So let me restate that. If these guys are in rolling contact, meaning they cannot slide, then the velocity at this point on that body and the velocity at this point on that body must be the same, which means all components in this direction are the same. So they stay in contact and they're not sliding, and which means their apparent velocities are 0. Okay, so if it's in sliding but they're in contact, only the velocities in this direction are the same, but these velocities will be different, and their apparent velocities will not be 0, but these apparent velocities will be 0. Okay, so let's do an example. I told you about this one. If you think of this point P on 3, then you could think of, well, what is its velocity? Well, first of all, you could use the velocity difference equation. You could say, what's the velocity of this point, VA? Well, it's obviously 0. It's stuck to ground. So you take VA plus omega 3 cross RPA, and that would give you this vector, which is the velocity of P3. Okay, so again, we just used the velocity difference equation. Velocity of this plus omega of this cross this vector gets the velocity of that. So we just march from that point to this point. Okay, and this almost, it doesn't look like it, but these is a 90-degree angle right here. Okay, so it's always 90 degrees from RPA. Okay, and what's the absolute velocity of P2? Well, we could do the velocity difference equation of this as well and do, what's the velocity of that? VB, well, 0. And then you add that to omega 2 cross RPB, and that gets this velocity, which is the velocity of P2. Okay? And again, this one and this have to be 90-degree angles. Okay? So you can see, here's the two, that's the velocity of P3 and that's the velocity of P2 at that instant. They're both coincident at that instant, but they have different velocities, which tells you right there, since they're not equal, they're not this, they're not just rolling. So you know they're sliding and rolling. You know they are in contact because they're touching there, which means that you can see the component along this common normal, which is here for this vector and here for that vector, must be equal so that they're touching. So you can see this velocity here is the same as this velocity here. It's a rectangle, so that they're equal. And that must be the case because they're in contact. But they're not, the total vectors aren't equal because they're not just rolling. They're rolling and sliding. And you can see that because the component of this here is different from the component of this here. Those have different velocities, and their apparent velocities would also be different. If you imagine an ant sitting on here as if it's not moving, this would be moving along the common tangent. Okay? So go through that. That's just an example to help you think of the difference between rolling and sliding contact and when velocities are equal and when they're not, and in what directions, along the normal or the common tangent. Okay, so this is a slide that can help you sort out what I've kind of taught. And it's a little trivial for velocity analysis, but there's going to be a similar one for acceleration analysis that's going to be very useful. Okay, so it's kind of broken. It's like a quad chart where the top row means you're talking about 2 points on the same body, like P and Q, and this bottom row is two on different bodies. And then the column is whether the points are coincident, and this column is whether they're separated. Okay, so let's look at the first case. If you have, this is the most trivial case. You can see in the top here, I don't know if you can see my laser pointer up there, but this is for the case where, say, you have two different points on the same body that are coincident. Or, sorry, I guess, well, yeah, two different points on the same body that are coincident. Okay, so that means, and say one of the points is Q, one of the points is P. Well, of course, their velocities are going to be the same because they're basically the same point. Okay, so just Vp equals Vq. Okay, but then if we go over here and we say we still have 2 points on the same body, P and Q, but now they're separated. See, P and Q are not coincident. Okay, they're separated. Well, then you need to use the velocity difference equation to get from one point to the next. So if you have the velocity of Q, you add that to the velocity difference vector, VPQ, which is omega of that link. In this case, it would be omega 2 cross RPQ, which is the position difference vector. So that's how you'd march from Q to P to find the velocity from Q to P. 2 points that are separated on the same body. Okay, but now say we go to, say we have two bodies. Okay, so it says on different bodies. So say there's a body 2 and 3, and say here's a pin in a slot. Okay. So now we have this body moving and this body moving on top of it, sliding in the slot, say. So two bodies, 2 and 3. But now we have 2 points on different bodies, but they're coincident. So this is P3 is coincident with P2, but P3 is on 3 and P2 is on 2. Okay? And at that point, when they're both coincident on top of each other but on different bodies, then the way you get the velocity is you take the velocity of, say, P2, and then you add it to the apparent velocity, Vp3, with respect to 2. Okay, so it's like the same thing as this is the velocity of the truck, this is the velocity of the baseball, you add them together, you get the total velocity of P3. Okay, so you can see how we go from two of like coincident points on different bodies, but then if you have this case where you have two different bodies and two different points, one on each body, that aren't coincident, then you have to use a combination of this and this to get there. So if you had the velocity of this, you'd use the angular velocity of this to march from there to there, P2, and then you use the apparent velocity to get from P2 to P3, then you'd go from P3 to this P using this equation as well. So you could march your way to point to find the velocities. Okay? Okay, so that's important. So now, those are just important principles, but now we're going to do an analytical method of velocity analysis that is analogous to the analytical methods we did for position analysis. Okay, so let's review. First of all, here's a slider crank mechanism. You can see here we drew the vector loop, and we did a vector loop equation. We made sure we could solve it. We wrote it out in component form. And if you recall from position analysis, we solved it, right? So there was, there's two equations, two unknowns. The two unknowns were theta 3 and R4. I gave you many ways to solve it. There was the brute force way of just, dot producting stuff and canceling stuff out and solve it by hand. And we got R4 as a function of theta 2 and theta 3 as a function of theta 2, where all the other things are just, constants. and that was the analytical approach, right? To do position analysis. Well, to do velocity analysis, if you didn't take this course, you would likely just say, well, great, now I have those, and I'll take the derivative with respect to time. Okay, so I do, V4 would be dr4 up there with respect to dt, so the derivative of r4 with respect to time. Or for convention, it's r4 dot. If there's a dot above it, that means it's derivative with respect to time in this course. And then you just say, okay, well then if I want omega 3, I take the derivative of that with respect to time, which is omega 3 dot. And you'd be right. That would be fine. You could totally do that, and you'd get the right answer. And it would, the answer would be a function of, all the constant link lengths and everything. It would be a function of theta 2, which you were already given for position analysis, and it would be a function of the theta 3 and theta 4, which you also know for position analysis. Or sorry, I guess this is the slider crank one. But all the other things you would know from position analysis. You'd know R4 from position analysis, and then right. But then I'd also have to give you an omega 2, and that's the new input. And then you could find V4 and omega 3, which is velocity analysis. So basically, that was a really long way to say you could just take the analytical equations and take the derivative with respect to time, and you'd have velocity analysis done. Problem with this approach is it's very difficult to take derivatives of very complex equations. And remember, these are actually really simple so far as mechanisms go. So you could imagine getting some really nasty derivatives and not being able to do this by hand in any reasonable amount of time. Okay, so not a good approach to use. You might think, well, a better approach is to take the component form of the equations. Remember how vector loops turn into two component forms, or two equations from the component form, and you can just directly take the derivatives of those with respect to time. And I encourage you to practice doing this. You need to be very good at derivatives, particularly of cosines and sines, and know what variable you're taking the derivative with respect to. So I put it on pause and try and take the derivative with respect to time, and try it yourself. But if you don't want to do that, I'm going to give you the answer because we're not doing this live. Okay, and the answer is this. Okay, so make sure you check your answer, and then the answer to this one is here. Okay, so again, I encourage you to try these, and if you're confused, brush up on just derivative math. Knowing how to take the derivatives with respect to various variables. Okay. So we could take the component form, take the derivative with respect to time, and then we'd have these two equations, and we could awkwardly solve for what we want. Remember, we want V4 and omega 3, and they would, of course, be functions of the same stuff, and they'd be the same answers. It's a different way to get the same answer, but it's a little less painful as the other approach I just gave you, but it's still painful, and I wouldn't recommend it. Okay, so a much smarter approach to use is the first order kinematic coefficients is the approach. Okay. So remember, I basically taught you can solve stuff by hand. I gave you some tricks to do it by hand for position analysis. Then I said, but the smarter way to do position analysis is with Newton-Raphson. And I taught you a systematic way to do that. Well, I just did the same thing with analytical approach for velocity analysis. It's analytically, you don't want to do it like that. You want to use this approach, first order kinematic coefficients. Okay. And before I teach this approach, you need to understand two principles of math. The first is the chain rule. Okay, so this is multivariable calculus. Okay, if you have a function of a variable, say alpha is a function of beta, but you want to take the derivative of alpha with respect to time, some different variable, well then you have to take the derivative of alpha with respect to beta times the derivative of beta with respect to time. So these two things can cancel, and you can get derivative of alpha with respect to time. Okay. So brush up on your multivariable calculus. You're going to need it. And then there's the product rule. So if you have two different functions here, and they're multiplying each other, and you want to take the derivative of it, well, what you do is you take this one untouched times the derivative of this one, plus this one untouched times the derivative of this one. So just memorize that. If you want to see the derivation, it's online, and you learn this in calculus. Okay. Okay, but if you trust me and know these rules, we can move on here. Okay. So if you're doing velocity analysis, here's what you do. Just forget about all that stuff about the stuff I just taught you about the analytical approach is what you would likely do if you didn't take this course. You just brute solve it times and take the derivative with respect to time. Don't do that. What you do is, you do the position analysis up to the component form, and you assume, okay, I've already done position analysis. You know for a given theta 2 what theta 3 and theta 4. So everything's known here, you assume, because you've done position analysis. You have to do position analysis before you do velocity analysis. But now I'm going to give you an omega 2. So I say at this theta 2, and you know it's theta 3 and theta 4. But now I give you an omega 2, and I want you to solve omega 3 and omega 4. What you do is you take the component form, and you still take the derivative of both of these, but you take the derivative not with respect to time, but the derivative with respect to the input variable, in this case theta 2. Okay? So if I took this equation, the first equation, the x components in the component form, and I took the derivative with respect to theta 2, then you're going to get an interesting equation. And again, I encourage you to put this on pause and get your derivative experience. But I'm going to give you the answer now, because you can unpause me. Okay? So you take the derivative of this, check my math. This is what you would get with this definition. Okay? So if you have theta 3 prime, that's called, this is a first order kinematic coefficient. Okay? And just go with me here, I'm just defining it. You put a prime on it. Okay? That doesn't mean it's some delta t later. That was our convention with prime. That was for displacement stuff. This time we're going to say if it's theta 3 prime, we're just going to define it as the derivative of theta 3 with respect to the input variable theta 2. Okay, so it's always with respect to the input variable is what theta 3 prime is. Okay, again, theta 4 prime is the derivative of theta 4 with respect to the input variable theta 2. Okay, and hopefully you can see that if you take the derivative of this with respect to theta 2, this is what you get with these two things plugged in. Okay, again, put me on pause and take the derivative of this again, and then I'll give you the answer. Okay? Okay, so the answer is this, where we use these again. Okay? So you might say, well, why are we doing this? Why are we taking the component form, taking the derivative with respect to the input? Well, you can see if we do this, we generate these first order kinematic coefficients. Okay? Theta 3 and theta 4 both prime. Well, what's the magic of first order kinematic coefficients? Well, we can solve them if we take this equation. So I'm just taking these two equations. I'm going to move them up here. There they are, same two equations. And now what I want you to do is solve for theta 3 and theta 4 by using linear algebra, matrix math. Okay? You could put it on pause, or if you don't know what I'm talking about, I'll give you an answer here. So what you do is you take everything in these equations and that doesn't have theta 3 or theta 4 prime in them, the first order kinematic coefficients, and you kick it to the other side of the equation, and then you pull them out in a matrix form. Okay, so these two things up there were kicked to the other side, and then you can see if I multiply this matrix, this vector, sorry, by this matrix, you can see I get those equations. So hopefully you can see how this is kind of the matrix form of those two equations. And it has to be a matrix because there's two equations. Okay? And so you could see once I move, once I put this component form into this matrix form, then I can take the inverse of this matrix, times it by both sides, and you can get the answer. But before you do that, I want to point out that this matrix may look very familiar to you, this particular one. It is the Jacobian matrix for a 4-bar. Okay, so every 4-bar, remember I said a Jacobian matrix when we did Newton-Raphson was kind of like a fingerprint or a signature mathematical fingerprint, right, of a mechanism. And for a 4-bar, the Jacobian is this guy. Okay? And it magically showed up in Newton-Raphson, if you recall, and it magically showed up in velocity analysis here. So it showed up in position and velocity analysis. And it's one way you can know if you're doing things right. If on an exam you do position analysis of some mechanism, you get a Jacobian matrix, and then you do velocity analysis, and suddenly a different matrix pops up, that means you made an error and you're wrong. Okay? So when you do position and velocity analysis and acceleration analysis, you'll find it pops up in that. It's kind of a confirmation to you that if they're all the same matrix and that they're the Jacobian matrix, and you're on the right track and you're correct. And remember, you know how to take the find the Jacobian matrix just from the component form, according to what I taught you in the first topic under Newton-Raphson. Okay. So, but anyway, so that's the Jacobian matrix, and you invert it, like I said. So J Jacobian matrix inverted times both sides. It gets rid of this, turns into an identity matrix, and now you have J inverse times this stuff equals the first order kinematic coefficients. So you can see through linear algebra, we were able to solve for them. Okay, but still, what's so interesting about first order kinematic coefficients? Well, from the chain rule, we can get what we want by just multiplying them by the input variable that we're given in velocity. So look, omega 3 is defined as the derivative of theta 3 with respect to time, right? But according to the chain rule, that's also the derivative of 3 with respect to the input variable times the derivative of omega 2 with respect to time, which is omega 2. So this is, remember, the definition of the first order kinematic coefficient, and this is the definition of omega 2, the angular velocity. And it's the same thing with omega 4. Okay, so once you find first order kinematic coefficients, you just multiply them both by the input variable omega 2, and now you have the velocity of everything else in the mechanism. Okay, so to review this approach, the first order kinematic coefficients, what you do is you take the component form that you got for position analysis, take the derivative of it with respect to the input variable, that's the key, not with respect to time. Through doing that, you'll generate first order kinematic coefficients, put the result into the matrix form. You better get a Jacobian matrix that tells you did it right. Then invert that Jacobian matrix to solve for the first order kinematic coefficients, and then multiply them by omega 2. And you're done. And it'll work for any mechanism. So we'll do a bunch of examples here. Okay? Okay, so say we have a slider crank mechanism. Again, we drew the vector loop. We did the vector equation. We had the component form. What we're going to do is take the derivative of these with respect to the input variable, which in this case was theta 2, right? And it usually is theta 2. Okay? Well, if you take the derivative of this with respect to theta 2, and again, you're always welcome to put this on pause. I recommend students do this a bunch, practice, because you get very good at it quickly, because you'll notice you're basically taking derivatives of a bunch of sines and cosines all over again. Well, you get the derivative of this with respect to theta 2 is this, where now we come up with a first order kinematic coefficient that's a little different. You see, with the 4-bar one, we were interested in theta 3 and theta 4. Those were angles. Those were thetas. And the derivative of those was like derivative of that theta divided by the theta input. Well, now we're taking the derivative of R4, which is a varying, it's a variable. This changes as theta 2 moves. But it's now the derivative dr4 with respect to theta 2. It's totally different units, but it's still considered a first order kinematic coefficient. So you put the prime there, it's R4 prime, and it's instead of a theta over theta, it's a displacement over a theta. Still first order kinematic coefficient, and it'll work. Whereas this theta 3 here is the traditional one we got from before, d theta 3 divided by d theta 2. Okay, then take the derivative of this one. Again, put me on pause to try, or I'll just give you the answer here. There it is. Okay. Now I would encourage you to take those two equations and put them into matrix form. Kick everything that doesn't have the prime first order kinematic coefficients to the other side, and then pull out the prime first order kinematic coefficients, and you'll have a matrix that should be the Jacobian of a slider crank. That's what it is right here. Confirm that this is the same equation as that for your own sake. And you will see, yes, indeed, that matrix is the Jacobian of a slider crank. You can invert it, which you all know how to do for 2x2 matrices. I taught you that in the last topic. And you solve for it, and then you just do the same thing. Once you have these values, you times them by omega 2 and you get the answer. Now, it's also worth noticing what these are functions of. Like this is a function. You might say, well, wait, I don't know theta 3. That's not an input variable. But remember, you do know it because you can't do velocity analysis until you do position analysis. And once you do position analysis, you know theta 3. And you know R4. You know everything from position analysis. Because I gave you theta 2, you solve for R4 and theta 3. You're done with position analysis. Now you do velocity analysis, and you depend on what you use to solve from position analysis, what you solve from that. And so